Capacitors are one of the most commonly used components in AC circuits. This presentation shows how capacitance affects AC circuits, including the relationship of current and voltage. It also introduces many applications of capacitors in circuits. Since capacitors are found in most AC circuits, this presentation is very important to an understanding of AC electronics. When you have completed this presentation, you will be able to describe commonly used capacitors, calculate total capacitance for capacitors in series and parallel, describe the phase relationships between current and voltage in different types of capacitor circuits, and calculate impedance in series and parallel RC circuits. Fixed capacitors are usually classified by their dielectric. Electrolytic capacitors use a very thin oxide film as the dielectric and have very large capacitance values in a small space. Mica capacitors use mica sheets stacked between tinfoil sections which conduct the current. These capacitors have a value of 50 to 500 picofarads. Paper capacitors use 2 rolls of tinfoil conductor separated by a paper insulator and rolled into a compact cylinder. These provide medium capacitance values ranging from 1/1000th to 1 microfarad. Many foil-type capacitors use a plastic film instead of paper for the dielectric. Ceramic capacitors use ceramic as the dielectric with a silver coating on either side of the ceramic. These capacitors have values of up to 1/100th microfarads. Variable capacitors often use air as the dielectric. Movable plates can be rotated to increase or decrease the amount of capacitance. This is the symbol for a variable capacitor. The standard ranges of capacitance range from 1 picofarad to around 100,000 microfarads. Tolerances of capacitors range from plus or minus 1% for small value precision capacitors to plus 80%, minus 20% for some ceramic types. Capacitors are also rated by voltage. The working voltage is the maximum voltage that can be applied continuously to the capacitor. The peak voltage is the maximum voltage that can ever be applied without damaging the capacitor. Larger value capacitors are usually polarized. That is, voltage can only be applied to them in one direction without damaging them. When capacitors are connected in parallel, the total value of the capacitance is equal to the sum of all of the capacitors. In this circuit, the values of the capacitors is 0.025, 0.005, and 0.010 microfarads. The total capacitance for the entire circuit is 0.040 microfarads. When 2 capacitors are connected in series, the total capacitance is calculated using this formula. Total capacitance equals the value of the 2 capacitors multiplied together, and this quantity divided by the value of the 2 capacitors added together. This is similar to calculating the value of 2 resistors in parallel. In this case, the value of the 2 capacitors is 200 picofarads and 500 picofarads. The total capacitance of the system is 100,000 picofarads divided by 700 picofarads, or 140 2.8 picofarads. Notice that this value is less than either of the 2 capacitors combined in series. A more general formula for two or more capacitors in series is similar to the law for parallel resistors. That is, the total capacitance is the reciprocal of the sum of the reciprocals of each of the capacitances. When a capacitor is placed in a direct current circuit, such as this, and the switch is closed, electrons flow from the negative terminal of the battery through the resistor to this side of the capacitor. Electrons are drawn from the other side of the capacitor to the positive battery terminal, placing a charge on the capacitor. During the charging process, current flows in the circuit, but does not actually flow through the capacitor. Instead, electrons flow into one lead of the capacitor and collect on one plate, giving it a negative charge. An equal number of electrons flow from the opposite plate and out of the other lead, giving this plate a net positive charge. In this way, current appears to flow through the capacitor, but does not actually flow across the dielectric. The amount of time it takes for the capacitor to charge or discharge 63.2% of the value of the applied voltage through the resistor is called the time constant. It is the product of the resistance and the capacitance. For example, the time constant of a 0.25 megaohm resistor and a 50 microfarad capacitor is 12.5 seconds. Thus, it will take a 50 microfarad capacitor 12.5 seconds to charge 63.2% of 12 volts through a 0.25 megaohm resistor. It will take the same amount of time for the capacitor to discharge the same percent of voltage. When a capacitor is located within an AC circuit, it charges in one polarity, discharges, charges in the other polarity, and then discharges again. Even though no current flows through the dielectric of the capacitor, the cycles of charging and discharging make an alternating current in the circuit that matches the frequency of the alternating voltage. As the capacitor begins to charge on each cycle, the amount of current in the circuit is maximum at first, then begins to decrease. When the current reaches zero, the capacitor voltage is at its peak. The alternating current then switches its polarity, and the capacitor begins to discharge. As the current reaches its negative peak, the capacitor is fully discharged and has zero voltage. Next, the capacitor voltage begins to increase in the negative polarity, and the amount of current again declines toward zero. When several of these cycles are examined together, they appear to be 90 degrees out of phase with each other. This is called a phase shift between the voltage and the current in the circuit. Capacitors oppose changes in voltage, and since the capacitor in an AC circuit is constantly charging and discharging, the capacitor is always opposing the change in applied voltage. The term for this opposition is capacitive reactance and is shown by this symbol. The capacitive reactance is inversely proportional to the capacitance and the frequency as shown in this expression. The capacitive reactance is measured in ohms. The frequency is measured in hertz. And the capacitance is expressed in farads. When a resistor and capacitor are combined in series in a circuit, it is called an RC circuit. In these circuits, The voltage source produces a voltage that fluctuates as a sine wave, which makes a current flow in the circuit. No electrons cross the capacitor, but a voltage is developed across it. This voltage lags behind the current in the circuit by 90 degrees. It is a function of the current and the capacitive reactance, which causes a capacitive voltage drop. The voltage across the resistor is in phase with the current in the circuit. The voltage across the resistor is a function of the resistance and the current. Kirchhoff's law states that the sum of the voltage drops across all of the components in a series circuit is equal to the total voltage. If at any one instant the voltage drops across the resistor and capacitor are added together, the resulting sine wave is equal to the applied voltage. The amount of the phase shift between the current and applied voltage is a function of the size of resistance and the capacitive reactance. It is always between 0 and 90 degrees. The values of the resistor voltage and capacitor voltage are added together by vector addition. This is the basic format used to draw vector diagrams used in vector addition. The first line on the diagram represents the current. It starts at 0 and extends to the right, indicating 0 degrees. Its length represents its peak value of AC current. The vector representing the voltage through the resistor is drawn on the same direction line as the current, since it is in phase with the current. However, its length is shorter, since its value is less. The voltage across the capacitor is 90 degrees out of phase with the current, so its direction is 90 degrees away from the current line. Again, its length represents the peak value of the capacitor voltage. To add the resistor and capacitor voltage to determine the applied voltage, a box is drawn from their respective values. And a line is drawn from the origin point to the far corner of the box. The length and direction of this box indicate the magnitude and phase angle of the applied voltage. In this case, the applied voltage is at 45 degrees, and it is longer than either of the added values, indicating that it is larger than either of them. The new line represents the hypotenuse of a triangle. Using Pythagorean's theorem, the length of the hypotenuse can be determined using this formula. The applied voltage is equal to the square root of the square of the resistor voltage plus the square of the capacitor voltage. The total opposition to current flow in an AC circuit is called the impedance. The impedance is denoted by the letter Z and is expressed in ohms. It is equal to the voltage divided by the current. There are two sources of impedance in the circuit, the resistor and the capacitor. However, these two quantities cannot be added directly because of the phase shift. Instead, the impedance can be expressed as the vector sum of these two quantities. On a vector diagram, the impedance is shown to be the diagonal line, representing the vector addition of the resistance and the capacitive reactance. It is expressed in this formula that takes advantage of the Pythagorean theorem as impedance equals the square root of the resistance squared plus the capacitive reactance squared. The amount of phase shift in a circuit is the function of the ratio of the reactance and the resistance. When the capacitive reactance is large compared to the resistance, the phase shift is large and approaches 90 degrees. When the resistance is large compared to the capacitive reactance, the phase shift is smaller and approaches 0 degrees. The exact formula for determining the phase shift is the phase angle equals arctangent of the capacitive reactance divided by the resistance. If the capacitor and resistor voltages in a series RC circuit are known, the phase angle can be calculated as the arctangent of the capacitor voltage divided by the resistor voltage. When current flows in an AC circuit, the electrical energy is converted into heat or mechanical energy, just as in a DC circuit. Power is a measure of this converted electrical energy. Just as in DC circuits, Watt's law can be used to calculate the power in a resistive load. Power equals voltage times current. Power equals current squared times resistance. And power equals voltage squared divided by resistance. In these formulas, the RMS value of voltage and current must be used. This graph shows the relationship of power to current and voltage in a resistive circuit. It shows that all three quantities are in phase with each other, and that power is equal to voltage times the current. Consequently, when the voltage and current are negative quantities, the power is positive, and the resulting graph looks sinusoidal with a frequency that is double that of current and voltage. The average value of power is the product of the RMS values of the current and voltage in the circuit. Since the current and voltage are 90 degrees out of phase in circuits with only capacitors, the power curve is both positive and negative. The average value is 0, so power is not dissipated in capacitive circuits. In circuits which combine resistors and capacitors, the amount of positive power generated is greater than the amount of negative power. Consequently, the power that is dissipated is due entirely to the resistance. When the power in a circuit containing both resistance and capacitance is computed using the formula power equals RMS voltage times RMS current, the result is the apparent power. It is apparent because the power is not dissipated by capacitors. The power dissipated by resistance is called the true power, and it is calculated by including only the resistance. The relationship between the apparent power and the true power is called the power factor. This formula gives an indication of the relative amount of resistance and reactance in a circuit. In a series RC circuit, the power factor is the ratio of the resistance to the total impedance of the series RC circuit. Circuits containing only resistors have a power factor of 1, while those containing only capacitors have a power factor of 0. When a capacitor and resistor are connected in parallel, the current flowing through the resistor is equal to the voltage divided by the resistance, and the current in the capacitor is equal to the applied voltage divided by the capacitive reactance. The total current from the AC source should be equal to the sum of the resistor and capacitor currents. However, they are out of phase by 90 degrees, so the total current is a vector sum of these currents. Note that the capacitor current leads the applied voltage, so it is 90 degrees ahead of it. The total current is determined by using this formula. Current equals the square root of the resistance current squared, plus the capacitance current squared. The impedance of a parallel RC circuit is the applied voltage divided by the total current. In capacitive circuits, the impedance Z takes the place of R in Ohm's law. Capacitors are electronic components that store electrical energy as an electrical field. This presentation has shown the effects of capacitors in AC circuits. It has discussed how to calculate capacitance and described the phase relationships in different types of capacitive circuits.